series, very heavy algebra. For most questions, aren't we going to use the ratio test as our main go-to guy? We spent almost all of our time doing power series, which are of this form, right? They have x to the n, most common one, but you can have x to the n squared, and I'm going to do an x to the 4n just to show you that that particular also includes. So we say that these ones are centered at 0, and they're very often called Maclaurin series. I remember mentioning that. This one is centered at x equals -4. And this one here is actually not centered at 1. It's actually going to be centered at 1/2. So these two here are examples of what are called Taylor series. And if it's centered at 0, it's Maclaurin. If it's centered at some other number, then it's called Taylor series. And almost to a man, every single question in this section is the same question. And that is, what's the radius and interval of conversion? And let's get started. I'm going to do this one first. This one's a little bit different than the typical centered at 0, 1. And the main difference is this 4n up here. And you might not think that it does that much, but it is going to, well, I've just decided to do something. Let me put a 2 to the n in there. That'll make it more obvious what it does. Otherwise, you won't notice what I'm trying to get at. So we're going to do the limit as n tends to infinity of the absolute value of an plus 1 over n. And our goal is to find out what that's equal to. And we are eventually going to get one of 3 situations. I'm going to pause on that for a minute. And let me tell you what the 3 situations are going to look like. When we do questions like this, the ones that are centered at 0, we are eventually going to get x less than, I'm making this number up, right? X less than 7. That's the kind of result that you get. And when that happens, then the radius of convergence is 7. And the interval of convergence will at least start off like that. But then we test the endpoints. If you do this one, you're going to get a guy who looks like this. And the radius of convergence will be 7. And then we'll get the interval of convergence. And that'll be a little bit more awkward to do, but essentially it'll be from -10 to 3. And we can show you later where that came from. And then the ugliest one is this one here. You might think I'm going to say, well, you're going to eventually get the absolute value of 2x minus 1 less than 7, which you will. You might get something like that, but that's not the end of it. You must have an x. You can't have a multiple of x. So this is what that will turn into. And that means that in this case, the radius of convergence is that. And the interval of convergence, you're going to have to trust me on this, will end up being that. So we're going to see these types of things happen in each of these. So I kind of have a kind of idea of what's going to happen when I finish doing this one. So back to our question. We're going to do the limit as n tends to infinity. If you do an n plus 1 on this, you're going to get 2 to the n plus 1 x, and here's the thing, you've got to be careful. This is not x. Well, this is not x to the 4n plus 1. If you're thinking that, I can understand why you're thinking that. That is not what it's equal to. If you bear with me for a few moments while I just mute things so I don't get background sound, I'll return to the thing. It's not 4n, big long pause, plus 1. It's 4 lots of n plus 1. Does that make sense? Every n gets replaced by n plus 1. And so the bottom is n plus 1. Now, Then you turn the other one upside down. So you get an n factorial, you get a 2 to the n, and you get an x to the n. Now the cancelling, you have to be a bit more careful. If this 2 to the n cancels out this 2 to the n plus 1, won't you be left with a 2? Okay. Now we've done a few factorials, so hopefully we'll get good at those. If you take that n factorial and it cancels with this n plus 1 factorial, what's left and where does it go? So n factorial on the top, n plus 1 factorial on the bottom, they're going to cancel out. What's left and where does it go?
1 over n plus 1.
Okay, so essentially on the bottom, like we said. Now, this cancelling is a little bit trickier because it would probably be a good idea for you to rewrite that guy like that. Okay, so 4 lots of n plus 1 is really 4n plus 4. So now when I cancel this guy with this guy, what power of x is left over? It's not just an x, which is what you typically get, right?
Is that x to the 4th?
Oh, sorry, this is a 4n. There we go. So x to the 4th cancelling an x to the 4n plus 4. What power of x is going to be left over in that case?
X to the 4th.
Yeah. So you put all this package together. Darn, I wish I hadn't done something, but that's okay. We have a 2, we have an x to the 4, and we have an n plus 1. Are you happy with the bits that are left over? Right. Now, in this particular case, which is a bit I'm unhappy about, but we can live with it, it's the right answer. Don't you then make n go infinite? And if you want to, I don't think you need to, but if you want to think of it like this, it might help you see what's going on. Won't that become 0 when you do brute force? So the whole answer is 0. Okay, now according to the ratio test, whatever the limit is equal to, as long as it's less than 1, things will converge. Isn't 0, because it's a fixed value, isn't it always going to be less than 1? So this would be a special case, wouldn't it? This would be that the radius of convergence is everything, and that the interval of convergence ends up being everybody. Now, can you pretend for a minute that the answer was 2x to the 4, which is what I was hoping this one would turn into when I created it? Wouldn't you have 2x to the 4 less than 1? Do you see that when you eventually get it down into that format, couldn't you easily have the answer as 1 over the 4th root of 2? You know, it would be a little bit uglier because of that. But that's what we got, so that's what I'm keeping. Let's try this one. This one is centered at 4. Ratio test going to work well. X plus 4 to the n plus 1 on the bottom, 3 to the n plus 1, natural log of n plus 1 times upside down guy, 3 to the n, natural log of n over x plus 4 to the n. So we're going to do some cancelling, and then whatever's left is going to fit in here, right? Anybody in the top cancelling out with something in the bottom, and tell me what's left over and tell me where it goes. So pick something to cancel, tell me what you get.
X plus 4, n to the n plus 1, cancel out x plus 4 and on the bottom. Left with, let's see, x plus 4 with a 1.
So x plus 4 left on the top. Okay, somebody else now. Find something else to cancel.
The 3n and the 3n plus 1, or the 3 to the power of n, I guess.
Yeah, I know what you mean.
Okay.
What's left over?
3 on the bottom.
There we go. And now we have a natural log of n over a natural log of n plus 1. Keep them together. And then everything that doesn't have an n, in this case, that. Great. Now, this bit is the only bit that really need to worry about because it has n's in it. And if you do the log, the limit as n tends to infinity of the log of n over the log of n plus 1, do you know what that number, and it's a number, it's not infinity. Do you know what number the limit is? It's going to be 1. Can you prove it with L'Hopital? You'd have to do L'Hopital twice, but trust me, it works. So I'm going to save some time and assume that we've done that. Just put a little L to pretend that I've done the whole thing, and we get that. So we now know, according to the ratio test, that the limit of the ratio is equal to that, and it's going to converge when it's less than 1. That does not mean the radius of convergence is 1. What I'm going to do is multiply both sides by 3. Do you see that we now have the correct value for the radius of convergence? This has to be x, not allowed to be fractions, not allowed to be 2x, right? It has to just be x. And so this, because I'm multiplying by a positive number, it's okay to do that. We now have a radius of convergence of 3. And we have an interval of convergence. Well, if you solve this, you have to solve an equation involving absolute values. So the absolute value of x plus 4 less than 3 means that x plus 4 is sandwiched between 3 and negative 3. If you then subtract 4 from both sides, you get that. So right now, the interval convergence contains any value of x between -7 and -1. So far, so good. And then a lot of people forget that we're only 2/3 of the way through. Because don't we now need to check separately the two endpoints because they may or may not converge. So that's the final part of this puzzle. I'm going to test what happens to this series, this power series, when x is -7. Well, you just take the series, replace the x by -7, and then, play about with it and see what you get. Well, -7 add 4 gets me -3 to the n. I have a 3 to the n, and I have that. We don't like numbers like -3 or negative anything. You should separate these out into the number and the other number. And very often when you do that, you'll get a cancel. And now we are looking at this series. I'm going to take some shortcuts, and I'm pretty sure so will you during your homework, which is okay, as long as you realize that in a test, a midterm, you're going to have to prove this. But we're just going to talk it through. We're not going to actually physically prove it. Do you recognize an alternating series here? Would it be fair to say that you can tell that this series is going to be decreasing to 0 and therefore it converges? Can we just say, I can tell? If an alternating series is decreasing to 0, it's going to converge. I have to prove that its limit is 0. I have to prove that it's decreasing, all that stuff. But trust me, it will work. And therefore, converging. Now I now need to test the other endpoint, which was -1. So my series becomes -1 add 4 to the n over 3 to the n log n. It becomes -1 plus 4, 3 to the n over 3 to the n log n. And again, you get the cancel. Now I'm looking at this series. First question, just looking at it. This isn't proof, but this is how we're going to do it. Does that series converge or diverge? What's your gut feeling?
It diverge.
It does. If you had to, and you would in a test, prove that, which of all the 9 tests that you know about would be the one that you would use on this series?
Comparison test?
Integral.
I would do a comparison. Oh God, who said integral test? Get out of there. You know my rule. You never, ever, ever do the integral test unless nothing else works. And trust me, the comparison test works, and the comparison test will prove it diverges, which means that our interval of convergence gets adapted. You can use -7 and you still can't use 1. So those are your two guys. Now I cut a lot of corners here because I never actually formally proved that that alternating series converges, and I didn't formally prove that that series diverges using the comparison test, right? So we saved another 5 minutes, but you would have to do, that as part of your deal. But in the homework, I'm okay because these questions take long enough that if you can look at that and yeah, it converges, and if you can look at that and say, yeah, I know it's going to diverge, and we can let that slide for those questions, but not for your test. Okay. Anything about that question B? A lot in it, but is there anything that you're not sure about? Okay, let's move on. Oops, to get some more paper. The third one is like the ultimate horrible version. Most questions are not anywhere near as messy as this one, which I guess is good. But we do need to know how to do them because they do happen. What makes this one kind of different from the other two? Do you notice this is 2x minus 1? So if you ever get a 4x plus 7, a 3x minus 10, that kind of look, it's going to be very similar to how I do this one. Right? So we're going to start with the ratio test. Now, an plus 1, that's going to be 2x take away 1 to the n plus 1, 2 to the n plus 1, n plus 1 squared times. You turn the guy upside down, you get the 2 to the n and n squared, and you get a 2x minus 1 to the n. And there's not an awful lot of difference in that line than you would have found in the other two. So that's good, right? There's not a lot of difference algebraically. Okay, let's go hunting. Find something in the top that cancels out with something in the bottom and tell me what's left. Go hunting. Who can you kill?
2x minus 1 would be left in the top.
Agreed. Some else can also go. Something in the top will cancel something in the bottom. One more thing.
We'll have a 2 on the bottom.
Right, those two cancel, leaves a 2 in the bottom. So what you're now left with is an n squared over an n plus 1 squared, which I'll separate from the things that don't have, right, an n in them. And I'm going to save some time, although you're not allowed to in the test. What will the limit of n squared over n plus 1 squared look like as n goes to infinity? You could probably tell just by looking, couldn't you?
1.
Yeah. So that means we got this guy, agreed? And the limit according to the ratio test has to be less than 1 for convergence. First thing I'm going to do is multiply both sides by 2. But the radius of convergence is not 2. Do you notice this doesn't have an x? Doesn't this have a 2x? So we've got to figure out what to do to both sides to get this into the format that it needs to be to get the radius of convergence. So what should I do to both sides to get the radius of convergence?
Divide by 2.
And if you divide by 2, you get that. Are you comfortable with the half? You know, everybody gets divided by 2. Now we're ready. The radius of convergence is 1, and that's just going to be 1 forever. The interval of convergence is a little bit more work. We need to solve when is the absolute value less than 1. And that's sandwiched between these two. If you add 1 to both sides, or add a half, I should say, to both sides, you get that, which means that the interval of convergence, at least right now, is any number between -1/2 and 3/2. Is everything flowing reasonably logically right now? I mean, the more that you do, the kind of more mechanical this process becomes. And guess what? Yep. I'm now going to test the 2 endpoints. So let's see what we get this time. I'm going to test what happens when x is -1/2 in this power series. Well, you're going to get sigma n equals 1 to infinity 2 times -1/2, take away 1 to the n, over 2 to the n squared. It's a little bit interesting. That is -1. Is that? Yeah. And -1 take away -1 is -2. So I'm going to get -2 to the n over 2 to the n over n squared. I had to think about that for a minute. Don't like numbers, separate them out. And very often, just as happened here, when you do that, you'll get a cancel. Do you recognize an alternating series? We're not going to prove it, but you should. Converge or diverge?
Does it converge, right?
Yes, so converge. So we've got to converge. That's good. Now we're going to test the other side. And the test is 3/2. So our series, our power series, is going to be 2 lots of 3/2, take away 1 to the power of n, right? 2x take away 1. And on the bottom, a 2 to the n squared. That's n equals 1 to infinity. That is 3. 3 take away 1 is 2. So you get 2 to the n. And you get that guy. You get your nice little cancel, which you expect to see. And you now are looking at this series. Does that guy converge?
No.
Yeah. Oh, I seen one nod and one no. 1 over n squared. If it was 1 over n, I'd agree with you, but it's 1 over n squared. That will converge. Right. If I wanted to prove that that converges, wouldn't I just say it's a p series, p equals 2, 2 is greater than 1, it converges. Right, do it in English. Great. 1 over n would be a p series, p equals 1, that diverges. But as long as it's bigger than 1, a p series will converge. So that means our interval of convergence is now, you can use -1/2 and you can use 3/2. Cool.
So, will they always have good cancellations, or is it just set up like that?
The way the math works, yeah, it's hard for me to think of one that wouldn't have a good cancellation, right? Have you noticed and at least in the ones we've got, isn't it like 3 to then cancels a 3 to then? It's that kind of cancelling. That's typically the most common, and the reason for that is because of this something to the n. Won't this turn into a number to the power of n? And that's probably going to cancel, more likely than not. So you should be on the lookout for it happening. So if it doesn't, be a bit worried. Anything else about these 3 examples? Because we've basically covered all the ones I want to, unless someone's got a homework question from that section that you didn't like, and I can do that as well. So you've got a template for every possible combination. This last combination is very rare, right? Most of your questions are not like this. The ones that you are going to be dealing with are more likely, you know, the x plus 1s and, you know, the x to the n's that we did yesterday. So if I don't have any questions or homeworks to do, I want to move on. Last chance. Okay.
Just one question.
Yes,
about
sure.
that last part.
Mm-hmm.
We would use the comparison test to
For this one,
for x equals 3/2.
I would just use a p-series test.
Oh, and that's enough work.
Yeah.
Okay.
So we are now moving on to next week's work. So that means what I'm about to do, as usual, will not be in the test, right? Which, by the way, is visible now. It's in section 911. And we're going to be looking at creating power series. Right, so right now they've just appeared, right? Like out of magic. Here's a power series, right? Although I did show you one, didn't I show you 1 over 1 minus x? You remember that guy? So I'm going to start with him. Can we assume, damn it, space. Let's do that again. Can we assume that 1 over 1 minus x is the same, or equivalent, probably a better word, is equivalent to this very nice power series? Remember, we proved it. And I think we also found that its radius of convergence is 1, and that its interval of convergence is -1 to +1, right? We did that as well. But I'm really only going to focus on this guy behaves just like this power series. So this infinite polynomial looks like that guy. And there's another one, which I'm not going to prove. So you would just memorize this. Just that guy. Are you good so far? So you only know right now 2 power series that are equal to a function. You know that this function is that power series and this function is that power series. And I'm going to use these guys as building blocks to create more power series. And that's what today, what's left of today, is going to be about. I'm going to create more power series. So let's show you how it works. I want to calculate a power series for that fraction. So it's only going to be fractions we're dealing with right now, right? Well, how can I do that? Well, you do some rather interesting algebra. Would you agree that x cubed over 1 minus x is x cubed times that guy? And I know the power series for that guy. Actually, can I change that to 0? So far, so good. Now I'm going to show you some algebra using sigma. You are allowed to multiply and divide, and you're allowed to factor out and bring factors into sigmas. And the way that they can be manipulated, I think, is relatively straightforward. That's my wife arriving and the dog's telling us. Does that seem reasonable that you could just bring in the x cubed to the sigma? Does that seem logical? Because that's what you can do. And then you can do a different piece of algebra, which basically says if you have 2 powers of x, you can multiply them together. Doesn't that mean you just add their powers? And guess what? We now have a power series for that fraction. So far, so good. Now watch what I'm about to do. I'll put it in red. I'm going to put a 4 there. So I'm going to do the power series for 4x cubed over 1 minus x. Well, that's going to be 4. That's going to be 4. That can be pulled in as a 4. And that's a 4. Do you see that it almost did nothing different, wasn't it? It's just part of the same flow. That's kind of cool, isn't it? You can do that. Here's a different situation. I want to get a power series for 1 take away 3x. And I'm going to use this guy because this guy looks very like this guy. But this time I'm going to use substitution. And substitution is big in these questions. You do it a lot. You know that that x and that x are basically placeholders. I could put anything I like there, and as long as I put the same thing there, it's okay. So can you imagine that this x was substituted with a 3x? Then wouldn't I just need to substitute this guy with a 3x? And guess what? You are allowed to do that. Does that seem logical? And of course, we have a style point rule. And the major style point rule is the x's have to be in their own. Does that make sense as well? That 3x to the power of n can be written as 3 to the n times x to the n, right? Giving each one their own power of n, essentially. So far, so good. So let's put the package together. I want to do x squared over 1 take away 4x. I want to do a power series for that fraction. So I'm going to take the x squared out of the equation. And I'm going to focus on just getting the power series of this guy first. And then once I figured that out, then I'll multiply it by x squared, right? So this x squared is just going to, stay there for a while. Let's just focus on this guy. 1 over 1 minus 4x, doesn't he look like this guy again? And won't I do a same kind of substitution? But this time I'm going to use 4x. So we are going to get sigma n equals 0 to infinity 4x to the power of n. Then I'm going to do some style points. It's going to be 4n x to the n. Okay, what do you think I'm going to do next?
You merge the x squared and xn together.
Right. Now, if you do it enough times, you can save a line of working. So I'm going to see if I can save this line of working and you're comfortable with it. Are you comfortable with me just doing that right away? Essentially just adding 2 more to the power of x's. And guess what? We now have a power series for that fraction. Looking good? Oh, since I've got it here, suppose I put a 3 there. Won't that be a 3? Won't that be a 3? Won't that be a 3? And doesn't a 3 just appear here? You might have to put a little bracket around that so people don't think it's 34 to the n, right? So do you see multiples don't really do much? I mean, they're easy to handle. So I want to do x cubed over 1 take away x squared. No clues, no help, no pressure. You've got 90 seconds. Go for it. Find the power series of that guy. Figure out your own way of doing it. You were correct, Caleb.
Is it x to the 2n plus 3?
Oh, I'm not telling you. I will, but not yet. Because we still have a few seconds. Jessica, do you feel up for doing part of this?
Yeah.
Okay. What should I write?
X to the third times 1 over 1 minus x
Oh.
squared.
Correct. I'm jumping ahead here. You were right. I was wrong. Okay.
Or did you want me to give you?
No,
the
just keep
final
going. No, yep. Just tell me the working.
Okay.
If you can recollect it.
And then x cubed times the sum of x squared, or x to the 2n.
Okay. You are really on top of things because you're combining 2 lines together, which is nothing wrong with that. It's an efficient way of doing it. Agreed.
Okay.
And well, you're there, finish it.
Okay. And then the sum of x to the 2n plus 3.
And I believe that's what you said, wasn't it? Thomas? Was it Thomas? Can't remember who it was, right? So yeah. Do you feel comfortable about how we can actually create lots and lots of power series by only knowing what a couple of power series is? So let's put this one into the mix now, because I haven't used any that look like that yet. So I would like to know 4x over 1 plus x squared. And I know that a lot of you are getting pretty good at these guys, so you might not write that line down, but I will. Now 1 plus x is this guy. 1 plus x squared looks very like him, so I know I'm going to be using a version of this power series, right? But aren't I going to do a substitution of x squared instead of x? So that is going to give me an, oops, almost forgot, a -1 to the n and an x squared to the n. So I'm now going to have a 4x, n equals 0 to infinity. I'm going to have a -1 to the n, and then an x to the 2n. Are we cool with that? And if you bring in the 4 and the x, basically just to finish the puzzle off, you get -1 to the n, 4. I probably should put the 4 there, but too late now. X to the 2n plus 1. Does that look good? Bring an x in, get 2n plus 1, bring the 4 in. It's just a 4 on its own, right? If you really think there's a confusion, just stick a bracket around it if you want to emphasize that something is just a 4. Any problems? This has went smoother than it has in other courses in the past. Either I'm getting better at doing this, which is highly unlikely, or you lot are getting better at understanding it, which is nice. I like that. I don't have any problems with that. So if I give you any question that kind of has this kind of shape to it, are you comfortable about, at least up to the versions I've given you, you feel comfortable about how you would find a power series?
Yes, sir.
Cool. Okay. So let's put the cat amongst the pigeons and show you something that doesn't look right, but you have to fix it. That doesn't look right. That should be a 1, because that's the only guy in town. And I can't use this until he looks more like that. I can use it if it's 1 minus x squared, right? I can use it if it's 1 minus 5x, right? I can use it as, but doesn't that always have to be 1? And this darn thing is not right. It looks wrong because it, well, it's not, the question's wrong, but it looks wrong. So we have to figure out an extra line when this happens. So when this number is not 1, you will need to do the following. Has anyone an idea what I'm about to do next?
Divide top and bottom by 4.
Ooh, the 4 is definitely in there, and it might be what you're saying. I'm just maybe not hearing it, right? But we're going to do that. And that's what Jarrett was thinking, right, Jarrett? Right, so we are ready to rock and roll here, because can't we now use this, but with a quarter x, right? So this is going to be, and you don't need this line, I'm just doing this for overemphasis. Right, can't you think of this as a quarter times that, right? Just emphasizing the 4, right? Moving it out the road so it doesn't get in the way of things. So it's now going to be 1/4, and this fraction is now going to be this guy, right? But with a quarter. So far, so good. Right, 1/4, this guy goes here. Now let's make it still points. I'm going to call this guy x to the n over 4 to the n, because I think that's nicer looking than a quarter to the n, x to the n, right? You comfortable with that? I'm almost finished here. What's the only thing left to do? We're virtually there. The answer's in front of us with 1 extra step. What's the last thing I need to do?
Just bring in the quarter.
Right? And because of the way I've written it, do you see it plays well with the bottom guy? So do you see why you get an n plus 1 there instead of an n? Are we good with that? Now I'm going to change this guy to x to the 4. And that makes this guy x to the 4, which means I bring this guy out and we still have this guy, which means I have an x to the 4 here. I have an x to the 4 here. And when we bring this inside, we get that. You see that that x to the 4 really didn't do that much to the process. Right? Let's try another one like this. Let's try x cubed over 2 plus x. Which means I'm going to be using the bottom one, agreed? Because it's a 2 plus x, not a 2 take away x, right? Also, don't I have to take care of that pain in the butt too? So I'm going to call this x cubed, pull out the 2, and get 1 plus a half x. So far, so good? I'm then going to separate it as an x cubed over 2 and a 1 over 1 plus a half x. You comfortable with that? This x cubed over 2 is just going to stay there for a while. This guy here is going to get replaced using a substitution, and the substitution will be that this half x, it goes here. So it's going to be the sigma n equals 0 to infinity, -1 to the n, 1/2 x to the n. Are you good so far? Still with me? You know the next few lines are just making it pretty, right? What I call style points, right? I'm not going to do anything with the x cubed over 2 yet. There's other things that need to be done before that. What would be a better way to rewrite a half x to the n so that it's going to play well and look nice when we're finished?
Just write it as 1 over 2 and 2 to the power of n.
Okay. You comfortable with that? Now, pretty much finished. Don't we bring the little leftovers, because that's really all the things are, and you bring them inside. So you're going to get an x cubed joining that guy, which is an x plus 3. And this 2 is going to join that guy, and that's going to get me 2n plus 1, and we are done. Now, from very, very simple building blocks, aren't these fractions getting uglier and uglier? And yet we're still able to, within certain realms of usage, we're now able to get power series for quite major looking fractions.
Hey, can you put that paper back on the left side?
There we go. Do that one again. Bit messy. It's going to be my last one of this type, so obviously I'm going to have to make it messy. Might not look particularly ugly, but this one's probably the ugliest one that we've done. 10x on the top, 3 take away 4x in the bottom. Right? And that guy eventually is going to be a power series. Is it okay to take this away? Not yet? Okay.
Yeah, go ahead.
All right. Now, this guy looks like the top one. I know he's not a lot like him, but isn't he more like the top one than he is to the bottom? How do I know? Isn't it that little negative tells me? Okay. So this guy is going to somehow or other become this guy. So that means I'm going to have to do a fair amount of work to get there. What number shall I pull out as my common factor on the bottom? Because it could be 3 or it could be 4. That would be the most obvious choices. But
I
only
go with
one
the
of them
3.
is right.
I go
Why
with the
did you?
3
Why would you
Because-
go with the 3?
because it is a form 1 minus x, and we need to have that 1 in there.
Right. This has to be 1. That doesn't need to be 1, right? This has to be 1. That's why the 3 was picked. So if you have a choice, always say to yourself, what do I really need? I really need the 1. And that'll make up your mind that in this case you're pulling out 3. Now I'm now going to separate them out. Again, maybe you don't need this line, but I'm doing it. Right. Now at this point, can't we use substitution? And all we need to realize is that this x is right, this x here is going to get replaced by 4/3 x. So it's going to be 4/3, oops, x to the n. Agreed? Now style points. Make it look pretty. That's going to be 4 to the n, x to the n over 3 to the n. You all happy about that? Everybody gets their own power of n. Now let's bring everybody, the leftovers, let's bring them inside. The 10, I think you probably need to put a bracket around it so that you can do a 4 to the n, so that you can do an x to the n plus 1, and then you can get a 3 to the n plus 1. I know that 10 with a bracket around it looks ugly, but if you don't, couldn't it look like 104 to the power of n, and people wouldn't be 100% sure which we're talking about? I guess you could do 10 multiplication sign, but isn't that little dot sometimes easy to miss? So it's better to overemphasize than to emphasize it, right?
Could it be placed in front of the sum sign?
We like everything to be inside. So
Okay.
the style point rules is 1 big sigma. Whenever possible, in almost every situation, it will be possible. Right. And I just thought, not a new question, but I just thought of a style point thing that hasn't happened in my choices, but I have seen it before. Can you imagine that we got that, right? Imagine you got power series and we got that. That could happen, right? And you would be quite happy, I hope, in realizing that it looks good and that you would say, I'm finished, but I can do better. The only thing in that list of 3 things that really is changeable in any meaningful way is 8. Can you think of another way to write 8?
2 to the 3rd.
And because the bottom has a 2 to the power in it, isn't it worthwhile doing that? Whereas if it was 27, there's no point in me calling it 3 cubed, right? It doesn't bring anything to the table. This 2 cubed, which is another way of writing 8, won't it interact with this guy in the bottom? And won't the interaction be to remove 3 from here? So what happens if you take n plus 1 and you remove 3 of them? What have you now got? N plus 1 take away 3. What have you now got?
N minus 2.
Yeah. And would you agree? I hope you do, because I want you to agree with me. Would you agree that that's prettier looking than that? Prettier means simpler, in general, that's what it means. Cool. So let's move on and look at a different power series. Right now, this is magic. I'm just telling you that the power series for e to the x is x to the power of n over n factorial. And you can say, no, it's not. But I'm going to say, yes, it is. And after 5 minutes of arguing, you're just going to get fed up and agree with me. Yes, it is. E to the x is that infinite polynomial. Right? And I'm going to do a few quite interesting things to try and convince you now that it is in fact e to the x. First thing, I'm going to do a sketch. Now I know how to sketch e to the x. I'm going to be using Desmos because I'm definitely not going to do this by hand. So I'm going to get Desmos set up in a few seconds. Now, you cannot write in Desmos an infinite power series. Right? I wish it could take sigma, but ain't that clever. So I'm only going to be able to do some of the powers, right? I'm only going to be able to maybe do the first 3 or 4 terms. Now, in most power series, isn't most of the value of the function in the early terms? So we have a little formula, and it's called capital T for Taylor, and it's got a little 4 in it. And what that does is it's basically like S4 of x, right? You're doing the first 4 terms. Slightly out of sync here. N equals 0 gets you x to the 0, 0 factorial. Then x to the 1 over 1 factorial. Then x squared over 2 factorial. Then x cubed over 3 factorial. And finally, x to the 4 over 4 factorial. So when you are finding T4 of x, what you are basically doing is you are finding from n equals 0 to 4 of whatever the power series happens to be, right? So it's very close to the Sn, but you see, because we're starting at 0, there's actually 5 numbers here, not 4, right? That's okay. You can have 5 numbers. Now, I'm going to tidy this up a little bit. That one I'm going to leave to the end. X to the 1 is x, and isn't 1 factorial just 1? You agree? Isn't 2 factorial 1 times 2, which is 2? So that's x squared over 2. 3 factorial is 1 times 2 times 3, which is 6. And 4 factorial is 1 times 2 times 3 times 4 is 24. Will you just trust me that that is what you would get? Okay. Now, x to the power of 0. What is x to the power of 0?
It is 1.
It is 1. Now, this bit, you really do have to trust me. 0 factorial is 1. I can't prove it to you. I can only tell you it is true. A lot of things I cannot prove to you, right? If we did a few more calc classes after this one, I would be able to prove it to you. If you want to see a proof of it, look for a function called the gamma function. Look at online. It looks like a hangman symbol, right? That's what the gamma function looks like. And when you find the gamma function, you'll find that it's very closely related to the factorial function. But the gamma function allows you to find gamma of a half, and like half factorials, right? And 7/9 factorials, things you couldn't even, imagine what they would be. And if you do gamma of 1, you get 0 factorial. And gamma of 1 is described in terms of an integral, and the area under that gamma curve is 1. So that's the closest I'm going to get to proving it. You're going to have to do, if you're really, really one of those, I don't believe anything he says, that's how you're going to prove it. The rest of you are going to say, yes, okay, I'll trust you. So I'm going to put into Desmos, this guy, and I'm going to put in that guy. Now, if those two are equal, wouldn't this one be a pretty close fit to that one? And it's not going to be a perfect fit because didn't I stop at x to the 4, right? No, because it goes x to the 5, x to 6, x to 7, right? It goes on forever. But it should be a good fit. So here goes. Provided technology doesn't keel over and die on me, because this is dangerous. Y equals, we're on capitals. I have my little mobile one. Maybe I can use that. Yay, good. Much easier to do. Y equals e to the power of x. Great. Would you agree that's what y equals e to the power of x looks like? Okay. Now I'm going to adjust the window a little bit. I'm going to do the x's from -3 to 3. Right. Yeah, just so we can get a better view of it, right? I'm just tweaking the scales. Now, the guy that I had was T4. He was, got you here, 1 plus an x squared divided by 2. Oh, hey, it's already beginning to fit a little bit, isn't it? If I add the next term, which is x cubed over 6, oh, it's fitting even more. If I add the next term, which is x to the 4, over 24, I've got an idea and I've thought of doing this, so I'm about to do it right now. If you just use the first 2 terms, would you agree it's a horrible thing? If you use those 2 terms, it gets better. If you use those terms, it gets better. And if you use those terms, it gets even better. If I take these out, the red one is e to the x and the black one is T4. Have I convinced you that that power series, if you added enough terms, wouldn't it match e to the x? E to the x is an infinite polynomial. Power series, infinite polynomial. If I added one more term, which is x to the power of 5 over 5 factorial, which is 120. Oh, would you agree that I've nailed it for a big chunk of space? That is proof number 1. Are the doubting Thomases amongst you feeling more inclined now to realize that e to the x can be written as a power series? A little bit more. Right. I'm going to prove it a different way. This is my final proof, my second proof. F of x is e to the x. What is the derivative of it? Well, isn't it e to the x? Isn't that one of the nice reasons we have e to the x? Because its derivative behaves well. Okay. Now, as a power series, if I write down, and I'm going to leave it with all the factorials in it as well. So I'm not going to turn them into 2s and 6s anymore. I'm going to leave them as factorials. Forever. Right? So can you imagine this continuing forever? Then what would the derivative of this power series be? Well, derivative of 1 is 0. What would the derivative of x over 1 factorial be? Wouldn't that just be 1 over 1 factorial, which is 1? What would the derivative of that guy be? Well, wouldn't you multiply by the power and reduce the power by 1? So wouldn't that be, oops, excuse me. If you differentiated this term, the answer would be 2x over 2 factorial. If you differentiated this one, it would be 3x squared over 3 factorial. The next one would be 4x cubed over 4 factorial. And the next one would be 5x to the 4 over 5 factorial. I can simplify that a little bit. 2 and 2 factorial, doesn't that get you 1 over that guy? Won't 3 cancel out part of the 3 factorial, but won't you still be left with the 1 times 2, which is what? 2 factorial. Won't the 4 cancel out part of the 4 factorial, right? 1 times 2 times 3 times 4, and you cancel just the 4, but you're still left with the 3 factorial. And that 5 will cancel out with part of 5 factorial. It will still leave 1 times 2 times 3 times 4, which we call 4 factorial. And would you agree that that guy is him? Agreed? That if you differentiate this power series, the answer you get is the power series that you started with. And isn't e to the x one of the few functions that has the property that its derivative is itself? Right? The only other function I can think of is f of x equals 0. Would you agree that is equal to itself when you differentiate it? But doesn't everything else turn into something different when you differentiate it? But not e to the x. So for the algebra minded people, about does that convince you that e to the x is a power series? Yeah. Okay. So if we assume, which we will, that e to the x is equal to this fella, then e to the power of 1, which is just e, won't that be the power series 1 to the power of n over n factorial? 1 to the power of n is just 1. I now have a way to calculate e. Isn't e whatever that series adds up to? Now, on our calculator, e is round about 2.718 in lots of digits. And I'm saying that this series adds up to e. Okay, how many terms do you want me to add up to see if we can get it close to e?
4.
So that's going to be 1 plus, I'm going to call 4, you finish in 4 factorial. So I guess it's 5 terms, but we can live with that, can't we? Right. That's 1 plus a half plus a sixth plus 1/24. Okay, let's see what we get. 1 plus a half plus 1/6 plus 1/24. And the answer I get is 2.708 and a lot of threes. Well, I'm good to the first decimal place. You agree it's matching that far? What could I do to get a better estimate? There's really only one thing I can do. What could I do to get a better estimate?
Add more numbers.
Okay, so how about add 1/5 factorial, right? Which means add on another 120th. So since it's there, I'll just say add 1/120th. And now I get 2.71 and a lot of sixes. Would you agree that I'm good to 2 and pretty close on the third one? If you get any doubt in Thomas's, let's do one more. 1/6 factorial. God in Himmel, what is 6 factorial? Well, it's plus, which is this answer, plus 1 divided by 6. And let's the calculator figure out what 6 factorial is. And the answer I now get, when you add that term, 2.718 and some stuff. So have you ever wondered, why is E 2.718 and stuff? Can you see that it was created by people finding the power series for E the X, i.e. finding this? And we're going to show you actually how to do that, which is quite amazing. And once you have a power series and you've checked it out, right, it works graphically, and you can find its radius and interval of convergence, can't you then just make X equals 1 and now you have E? And if I wanted to get E to 1,000,000 decimal places, wouldn't I just go to a computer program and just write a for loop for I equals 1 to 1,000,000? And I just keep on adding 1/20 factorial plus 1/2 million factorial, whatever it was you got to. And every time I did that, wouldn't I get just a little bit better answer? I believe, I'm maybe telling a lie now. It's either pi or E. There is a challenge out amongst computers to find out who can get the value of pi and or E to the most decimal places, right? In other words, you just get a computer program and it's a kind of test of how powerful your computer processor is. How many decimal places can you get pi to, or how many decimal places you can get E to? And it was a long time ago, but I think the computer that I remember the story for was called Big Blue. It was an IBM computer. I think its name was called Big Blue. And I don't know the number, but it got E to 2 million decimal places. And how did they do it? Isn't it just a matter of adding terms together? Now, what made it difficult for the computer is, don't you have to work to 1,000,000 decimal places to make sure your answer is correct to 1,000,000 decimal places? So that was the part that made it hard for the computer, because you had to write a program to work with huge accuracies. And that's where the power came in, because each time you added one, wouldn't there be 1,000,000 terms in the answer? 1,000,000 digits in the answer. So pretty powerful. I bet you today they've probably broken that record, whatever it was. And, you know, it's like 1,000 times bigger now. Once they've done that, I think they get bored doing it and they find some other quest. Like there's a quest out that I did read about a few weeks ago, where what they're doing now is, I can find a bigger prime number than you can. So what they're looking for is who can find the largest prime number, because prime numbers go on forever. Who can find the biggest one? And that's what they're doing in computing as one of the challenges. You don't get nothing for it, right? But you just get bragging rights, you know. So UCLA will say, hey, we won the prime number challenge. And then some place in Japan says, oh no, we're not going to stand for this. We're going to do better than you, you know, low competition maps. How are we doing, guys? I think this is a kind of natural place to stop, isn't it? We've just convinced ourselves at ease. I like to look at faces. And one of the things I noticed was puzzlement, disbelief, and I don't care. So I'm not sure which of those three I was picking up, but for me, it's so much fun. I mean, e to the x is a power series. Come on, you can't be amazed at that. You might have to be. It's just so cool. Okay, last name and bye-bye, and I'll hang about for questions. Kira, e to the x, cool.
It's pretty cool.
Very cool. What about you, Jessica? Cool?
I think so.
I think so. Thomas?
That's pretty cool.
Pretty cool, I'll do. I'll handle pretty cool. Cam?
Yeah, I liked it. It's cool.
Okay. You're just saying that because of what I did. You just don't want to say boring. Who wants to care what E is to a million decimal places? I got a calculator, it does it to E8. That's an engineer. You can tell them. Who needs a million bloody places? 8's enough. You can build a bridge with 8. Why do you need a million? That's what you're thinking. You just didn't want to tell me. See, a mathematician looks at that a different way. We look at it as, isn't that pretty? I mean, the power series for e to the x, isn't that pretty? It's such a, x to the n factorial. Right? Such an elegant, it is, it's nice.
Oh, come, you forgot to tell your joke.
I have a joke. Oh, yeah.
Yeah.
What's this joke, Cam?
Okay, 4 engineers get into a car and the car won't start. The mechanical engineer says it's a broken starter. The electrical engineer says the battery must be dead. The chemical engineer says there's probably a problem with the gasoline. The computer engineer says, hey guys, how about we get out and get back in?
Oh, good. Okay, gotta get my one back. An engineer and a mathematician were sitting outside a coffee shop, nice summer's day, and they look across the road and there's a big apartment building. And they're watching it, and 3 people go out. And then 5 minutes later, 1 person goes in. And they're thinking about it, and they said, the engineer says, well, what do you make out of that? And when the engineer says, well, I know there must be people living in that building, and there must be at least 1 person in the building because I saw somebody go in. And they went and said to the mathematician, well, what do you see? And he says, well, if 2 more people go in, the house will be empty. Oh, come on, do a math thing. Yeah. Cam's was better, right? Anybody got some questions, homework or others? That's what I'm here for. Now.
Can you go over the power series for the x to the n for as it y it may equals 1 over y minus x?
Sure. So,
Hey, let's go.
this guy is 1 plus, oh, let's put it on the screen. The power series of 1 over x is sigma x to the n. So your question is, could we go over proving that that's what it was, right? So I'm saying that it's this power series, right? Which we just write down as n equals 0 to infinity x to the n, right? So what I'm going to do is I'm going to say, let S be this power series. And I'm writing out longhand. Now, if I multiply S with X, in other words, I multiply all of this with X, 1 times X gets me X, multiply that, you get an X squared, multiply that by X, you get an X squared, and so on forever. And I'm just moved them slightly to the right to make it easy. So this is what S is, then X times S, won't it look like this, right? It'll just be a higher power. Then what you do is you say, well, I'm going to take the top guy and subtract the bottom. Well, if you take this polynomial, which is infinite, and you subtract this one, don't all of these cancel each other out, and all you're left with is 1. So S, take away X times S is 1. Then you do a bit of algebra, pull out a common factor. and then you divide. And so S is that. And what was S? S was this guy. And that's how you prove it. Now, if you wanted to prove 1 plus x, all you need to do is replace this guy with a negative x. I know the one you don't need, but I'm kind of emphasizing it. So when you split it, can you see why that generates a negative 1 to the n, x to the n? I just did a substitution where this gets replaced, right? This guy here essentially gets replaced like that.
Just to think about it, say if you say x is 2, down the one side would be 1 over 1 minus 2.
Right, well, you've got to be careful. This power series only has an interval of convergence between -1 and 1, which means you can only use it for values of x in that range. So if you try to use it with 2, you end up with a contradiction, a thing that doesn't work.
Okay.
And e to the x actually has an interval of convergence of everybody. Right? It works from -infinity to +infinity, which is another reason why it's so cool, right? That it, for any value of x, if you do enough terms, it'll fit.